So good evening, everybody. This is the first colloquium of the Department of Theoretical and Applied Linguistics in this fall semester. We are pleased to welcome everybody in this Zoom conference. We wish we could welcome you offline in the first humanities building of MGU, but at least the current situation comes with one advantage. We don't need our speakers to get on a plane to give a talk at the colloquium. Now, Alexey Sorokin will introduce our today's speakers. Alexey?
Dear colleagues, it's my great pleasure to introduce the speakers of the first NLP event on our colloquium. It's not just because it's the first NLP edition of this colloquium, but also because today we have really distinguished speakers, both by the width of their research interests and also by their scientific achievements. Our first speaker is Ekaterina Vylomova from the University of Melbourne. Her main research field is computational morphology. She also has some results on the border of computational morphology and computational semantics. She also has works on other sub-areas of computational linguistics, such as machine translation. And during recent years, she's one of the creators and the most active participants of the SIG-type computational typology initiative, where the first workshop will be held the next week on the EMNLP conference. And this workshop has been created mostly due to her constant and creative work. And also she's doing active work in the field of computational morphology inside the Universal Morphology Unimorph project. Our second speaker is Ryan Cotterell from the University of Cambridge and Technical University of Zurich. He also mostly works in computational morphology and computational semantics, but in fact, it will take me an hour to describe all his research interests, because they range from machine translation to some even algorithmic questions of NLP. And what impresses me more in his recent research is his ability to repose some questions which were studied in traditional experimental linguistics using some small samples of people, to reiterate these questions using modern big data, large-scale, multilingual approach. And actually, it will be easy to speak another 10 minutes about our today's speakers, but I think that in their talk, they will tell much more and more precisely and in more details. So I would like to welcome our today's speakers once more, and let's start.
Thank you so much, Lyosha, for such impressive introduction. So let me first share my screen. Do you see it?
Yes, it's okay.
Okay. So our talk is titled as The Secret Life of Words, Exploring Regularity and Systematicity. So the first part of this talk will be about modeling of morphological inflection. So since most of our audience is Russian speakers, so I'll try to provide more examples of on Russian morphology. So when a Russian native speaker wants to kind of make an impression to some like English speaker, they sometimes present something like this and saying about the like impressive richness of Russian language and kind of poor English morphology and the word lexicon. So, but it's not that simple, of course, because obviously all linguists know that English is analytic language and uses auxiliary verbs and prepositions, whereas Russian is syntactic and makes use of morphology. And if you look at these examples, so you'll see that it also mixes durational and inflectional morphologies. So there are some words that are novel, such as like убегает or бегающего and бег. So they are about word formation, whereas some other words are about word form change. So, and of course, duration and inflectional morphology, they present different levels of regularity and systematicity. And Bobby placed like on them onto continuous spectrum. So on one end, there was derivational morphology. On the other end, there was inflectional morphology. And of course, inflectional morphology, since it's more regular, so more researchers work on this particular type. And linguists described the paradigms, and of course in Russian. So there is a famous work from Andrei Anatolyevich Zalesnyak about Russian declension system. So, and nowadays, lots of knowledge is presented on Wiktionary. And in Wiktionary, we can see that there's an example of morphological paradigm table. So, and in this paradigm table for Russian specifically, it has two dimensions. One dimension is case, another dimension is number. And on the intersection, we can see there is a word form. So for those who did not work on Wiktionary, should note that these forms are not stored in Wiktionary, they are indeed generated. So if you look at the edit page of this table, you'll see there is a template, and there are some arguments that are provided for this template, so it can generate all the word forms. For instance, some type of declension and some lemma with stress pattern and some inherent features such as animacy. So here is an example of declension classes. So if you look at this particular template, so you'll see this description of the classes. And this is example from English Wiktionary. So if you look at Russian Wiktionary, so it's slightly different. So it follows the declension system that was described earlier by Andrei Anatolyevich Zalesnyak. So even for one language, there is different approaches how to describe the declension or conjugation systems. And of course, if we look at other languages within, for instance, English Wiktionary, such as Hungarian, we can see that the way they describe the case system also is slightly different. So suppose if you want to build a system that will learn morphological inflection or inflectional paradigms across languages and use just this English Wiktionary data, it will be really a bit challenging because there's no like universal system of cases, or there's no like cross-linguistically consistent annotation. So therefore, in 2016, we started a project called Unimorph, which is about the universal annotation schema for morphosyntax. So in 2016, John Silla Glassman spent about 3 months in a library, and he studied the dimensions of meaning, such as tense, aspect, mood, case, number, or animacy, and the possible features. So he decided to consider 23 dimensions as universal, and such dimensions have 212 features. And for Unimorph, we decided to take amorphous approach to morphology, which means that we do not take into account the morphological segmentation. So, and in 2016, a team from JHU, specifically Christo Kirov, they created a set of scripts that extracted the paradigms from English dictionary, and then we transform this data into the schema. And this sample provides a lemma, an inflected form, and responding text. This case is basically now accusative case and singular. So you may notice that we didn't provide any for adjectives. We see that there is a distinction between inanimate and animorph. So the task is quite simple. So if you have a system lemma and a set of target tags, such as noun, accusative, singular, so the system then is required to produce an inflected form, such as, in this case, Biglitsa. There was also variation of this task when instead of a lemma, you can provide some other form and its corresponding text, such as Biglitsami. Or the more challenging setting is when you just omit the text and just provide the form. So, and this year, so Alexei also participated in this shared task, and he submitted a rule-based system. So, but other teams also submitted, some of them submitted some weighted finite state transducer or CRF-based approaches, but the best performance systems were using some neural models, such as sequence to sequence. So I'll describe them briefly. So one of the winning systems from LMU, Munich. So they used the general approach that was taken from machine translation. So it has an encoder and a decoder. So the initial input sequence is provided as a characters. So the lemma is represented by characters and a sequence of tags. And so it's this sequence is then fed into encoder, which is bidirectional RNN with GRU units. And then there's soft attention applied on top of that. And then the decoder produces the output form character by character until it reaches the end of word symbol. So the system used ensembles of such models. And one of the winning settings was that they used enriched data sets. So they used not only lemma, but also they produced some other extra non-lemma forms, all their combinations. So the training data was significantly bigger. So, and we can see on this table for these 10 languages that in most languages, the performance is over 90%, and reaching for Hungarian, so which is typically treated as morphologically complex language, it's quite regular, and we see that it has over 99% accuracy. And for Russian, it's 91%, and the smallest numbers of accuracy achieved for Maltese. So the second neural approach that was proposed, it was based also on neural encoders decoders, but they also used first an external aligner. So they first extracted alignments between input and output strings. And then the neural network was trained to learn a sequence of operations. So since the morphological inflection is largely monotonic transduction, so it's this kind of approach is beneficial for this particular task. And we also refer to this as hard monotonic attention. So if we compare the three systems, so the one from LMU, MAD, and soft and hard attention, we can see that there is differences in performance for different types of languages. For instance, for suffixing and stem changes languages, so the hard attention model is performing the best, whereas for templatic languages, such as Arabic or Maltese, so the LMU system is better. So what types of errors they typically make? So here are some examples from the Aharonis model. So you can also check it online in their GitHub page. So for instance, instead of гляжу, it produced глядею, or instead of увлекаюсь, увлеклюсь, instead of зовет, звает, also instead of затьев, затей, instead of перстней, перстее, yeah, and instead of телекамер, телекамеро. So, and one of the challenges, as I mentioned before, is accusative case. So since the Unimorph doesn't provide animacy, so it's really challenging to differentiate between animate and inanimate forms unless you observed, say, singular. So if you want to produce plural, so if you did not observe singular forms, so it's almost impossible. So for instance, the system might produce labatriasi instead of labatriasov, and so on. So the next year, so we enriched the data set with up to 52 languages. And in addition to morphological reinflection task, we also organized paradigm completion. So in paradigm completion, the system is provided with full paradigms in the training data. And in the test, the system has to make prediction about certain lexemes that it did not observe in the train. So, and we organized it in different settings. So low, which corresponds to just having 100 samples. So there are 100 rows in the training data. Medium, which is 1,000 samples, and high, which is 10,000 samples. So, and as we can see, again, for high resource, so almost all neural systems are the best performers. If you look at low, there's a significant drop of performance, especially for instance, in Basque. So you have just 20%. And the best systems, like the LMU one that I described earlier, and there is another one, which is from UZH. So this is the system that was built on top of kind of modification of the Aharoni and Goldberg, where they enriched this model with extra operations such as copy, because the copy operation is very common in morphological inflection when you need to copy part of the stem, for instance. And there is another modification of this model that also used extra edit operations. So here's an example what the model was trained on and what it was producing. So based on these two systems, we decided to basically study what kind of errors they make and make some taxonomy. So we identified 4 general types of errors, such as target, silly errors, allomorphy, and spelling. So the target errors, they have, for instance, that might be free variation error. So when more than one acceptable form exists. So this is common for languages that have less standardization. So extraction errors refers to the errors due to unimorph parsing. So for instance, incorrectly parsed paradigm tables. Wiktionary errors refers to the errors that just come from Wiktionary data itself. There are also silly errors, so some kind of weird or bizarre errors. So for instance, producing mumbled instead of mailed, or when the system enters certain like an infinite loop of just some repetitions. So one of the errors that might be of particular interest to linguists is allomorphy. So it's misapplication of existing allomorphic patterns. And also there are some spelling errors when the prediction is correct, but there are certain like orthographic conventions that are not followed. So if you look at the distribution of these errors across these two neural systems, we see that allomorphy is the most common type of error. And what type of allomorphy error exists? So for instance, there might be problems with stem final vowels in Finnish, or ablaut in Dutch or German, plural suffixes or verbal prefixes in German, years in Polish, or genitive singular suffixes in Polish. Also, there's problems with animacy prediction in Polish or Russian. So it's hard to distinguish between gruzin and magazine if you did not observe any other form. Aspect, so misapplication of the future tense forms, and internal inflection in Russian compounds. So some of the dictionary data is not just a single word, but there's some concept that requires some dependency information in order to be inflected correctly, such as легкая промышленность. Another case is hyphenated words, such as государство донор. So the next year, so we organized another morphological reinflection task, and now on 103 languages. So at this year, again, the system from the UCH, from Peter Makar, was performing the best. And again, if you look at the accuracies, we see that it's the best for instance, the Pashto almost gets 100% for Polish. It's quite high accuracy. So, and in 2019, so we decided to try something new. So with an experiment with crosslingual transfer. So we basically provided a pair of languages. So one language was high resource, another language was low resource. Low resource means that we only provided 100 samples of inflections for that language. And for high resource, it was 10,000. So here's an example for Spanish and Asturian. So Asturian is low resource and Spanish is high resource. So some of the pairs, they consisted of related languages. Some of the pairs have completely unrelated languages. So, and if you look at the accuracy and Levenstein distance between the predicted form and the gold form, so we see that CMU system performed the best. And if you look at the pairs, so for instance, if you want to train our system to learn Kashubian, so it's clearly that Polish and Czech are more informative than, say, Latin. And one of the systems that performed the best was described by Antonis Anastasopoulos and Graham Newbigg. So this system used a lot of hallucinated data for low resource languages. And they also used an extra encoder for the sequence of text. So typically the previous systems used just a single encoder and single decoder. In their case, they have a separate encoder for the text sequence. So, but the major accuracy gain came from the hallucinated data. So what does it mean? They basically produce some kind of nonce words by first aligning the lemma and the output form and identifying the stem parts. And then they replace the specific characters in this stem, random characters, with some other ones. So the forms obviously did not exist in that language, but it helped the system to learn certain types of patterns or operations such as copy. So, and in this year, so we decided that we'd like to add some more linguistic diversity, because so far most of our languages were either Indo-European or Uralic.
Ekaterina, I'm terribly sorry to interrupt. It looks like something happened to my Zoom. It downgraded to the basic version, so we'll have to reconnect in a minute because the 40-minute limit applies.
Okay.
So it will kick us out in less than a minute. I'm sorry. I apologize about that.
Okay.
Yeah. Good.
Is it okay?